Here in this video, we would like to talk about what happens if the two rods are connected in series in the case of thermal conductivity. Let us consider two rods as I am going to show now. This is rod 1. I am intentionally drawing a thicker rod so that we can notice easily. In practical life, they need not be that thick. Assume these are the two different rods. These two different rods assume are made up of different materials, therefore their coefficient of thermal conductivities are different. This kind of a connection is called as a series connection. End of the first rod is connected to the beginning of the second rod. This kind of a connection is called series connection. Like, it's similar to the resistors connected in series, like that. Now, let's assume you supply the heat here this way. So, whatever the heat that you supply per second will first flow through the first rod. Then it has no way other than flowing to the other rod. So what we can say, dq by dt that's happening to the first rod equal to the dq by dt that's happening to the second rod. So what we need to understand carefully is, in series connection, rate of flow of heat is same. Rate of flow of heat is same. But I want you to understand carefully that as heat flows from place to place, temperature variation happens. That means if at the beginning the temperature is T1, everywhere temperature need not be the same. Temperature is different at different places. We can call the temperature as theta 1, theta 2 and theta 3. If you notice little carefully, one more important point that what we can get is the temperature difference between the first end and last end, theta 1 and theta 3, can be written as temperature difference across the first rod, theta 1 minus theta 2, plus temperature difference across the second rod, theta 2 minus theta 3. So what we are saying is, the total temperature difference is temperature difference across the first rod plus the temperature difference across the second rod. See what happens? First rod total system means theta 1 minus theta 3, first and last. Across the first rod means temperatures across the first and last of first rod. Across the second rod means temperatures across the second rod, that is theta 2 and theta 3. If you notice carefully, little carefully, this is minus theta 2. This is plus theta 2. Both of them will cancel. Then theta 1 minus theta 3 is only remaining. Therefore, this is very much valid equation. So, theta 1 minus theta 3 can be written like temperature difference across the first rod and the second rod. But we shall write the definition of the rate of flow of the heat. dq by dt is Ka delta theta by L. That implies delta theta can be written like dq by dt. Take the terms to the other side, right? Or before going to that, I can write delta theta by L by Ka. As I told you in the previous video, L by Ka is called as thermal resistance. So you can say dq by dt is delta theta by R. So delta theta, where R is called as thermal resistance. We have already discussed this in the previous video. Thermal resistance. Thermal resistance is L by K and A, where L is length, K is coefficient of thermal conductivity, A is area of cross section. So we can write, taking that into consideration, delta theta can be written like dq by dt. So dq by dt divided by L by Ka. So I will write it again for you for your convenience. Yeah. This part of the problem, this part of the equation, I will write it once again so that you can understand easily. Rate of flow of heat dq by dt is K area delta theta by L. delta theta can be rearranged like this. L by Ka can be written as delta theta by resistance is dq by dt, rate of flow of heat. So delta theta can be written like rate of flow of heat multiplied by thermal resistance. Now let us use this relation. We know the temperature difference across the first and last is temperature difference across the first rod, theta 1 minus theta 2, and temperature difference across the second rod, theta 2 minus theta 3. But as I told you, dq by dt is same. So theta 1 minus theta 3 can be written as delta theta dq by dt multiplied by total resistance of the system. You can call the total resistance as R series. As for this formula, dq by dt is again, dq by dt is same in series. Resistance of the first one could be called like R1. Second one could be called like R2. That is dq by dt of R2. As in series connection, rate of flow of heat is same, dq by dt can be cancelled. That implies R series can be written like R1 plus R2. That is similar to the electric resistors we have derived. So thermal resistance in series can be identified as R series equal to R1 plus R2. Whereas in the place of R series, I can write L series by K series and A, because that's the meaning of R, right? L by Ka, we have called it like R. R1 means L1 by K1A. We can say areas are different, so A series, A1, these areas are different. Let me call that as A1, A2. R2 can be written like L2 by K2, A2. This is the relation that we can derive and use as and when it is required. Now, if you try to simplify this equation further, if I assume a particular case like if area of cross section is same for both of them, we can write A1 equal to A2 equal to A series itself. We can also write if lengths are same, two wires are having the same length, we can write L1 equal to L2 equal to L. Putting all that in these equations, we will get further as from this equation, say equation number 1, L series means length of this one and length of this one together. So L1 plus L2. But else I have assumed it like same. So in the place of L series, I can write L plus L. By K series, I want to find out A series is A itself, because I have assumed that all areas are equal. That a particular condition I am trying to derive, equal to L1 is L, K1, A1 is A, L2 is L, K2 and A. So L by A can be cancelled on both the sides. This is L and L, that is 2L. 1L is cancelled here. So 2 by K series can be written like 1 by K1 plus 1 by K2, K1, K2, K1 plus K2 when you simplify, that is 2 by K series. So K series is 2K1, K2 by K1 plus K2. That's the derivation that we have made. But I want you to understand carefully, very carefully, that this is valid, this equation is valid only when these two conditions are satisfied. What are the two conditions? They have equal areas and they have equal lengths. Otherwise, this formula is not valid. We have to just use this formula and simplify and get it. Use this basic formula and simplify and solve the problem. So this particular one is valid only when areas are equal comma, lengths are equal. Thus, we are able to find out what is the effective resistance is, thermal resistance is, what is the effective coefficient to thermal conductivity is when two rods are connected in series. Next, we will talk similarly that what happens when they are connected in parallel. But most important part in series connection is rate of flow of heat is same in both of them, but the temperature is distributed. That's the most important point of series connection. That's it. Thank you for watching.